Hey everyone, welcome back to Chem Story. Today we're going to talk about condensed structures. It's a simple and efficient way to represent organic molecules without having to draw out every single bond. There are lots of ways to show the structure of an organic compound, but the condensed structure is one of the most straightforward and compact. So let's dive in and take a look at how it works. The condensed structure is basically a simplified version of a Lewis structure, but like anything simplified, it has its limitations. It works really well for relatively simple molecules, especially ones with long chain-like structures. But when it comes to more complex molecules, it can get a little tricky to represent them clearly using just the condensed form. In those cases, a bond-line structure, which we'll talk about in the next lesson, might be a better choice. So overall, the condensed structure is most effective when you're dealing with linear compounds, where atoms are connected one after another in a straight sequence. Now, here are a few key things to keep in mind. Single bonds are usually left out, and atoms are just written in sequence. Multiple bonds, or bonds involving heteroatoms, might still be shown. Just to keep things clear, lone pairs are not shown in condensed structures. And when the same substituent shows up more than once, we usually use parentheses to group them together. Let's look at how to convert Lewis structures into condensed structures, using a few examples. Take N-butane, for instance. That's C4H10. In its Lewis structure, we draw out all the bonds explicitly, showing every single hydrogen connected to each carbon. But in condensed form, it's written like this: CH3, CH2, CH2, CH3. Here, each carbon is written together with the hydrogen atoms that are attached to it. Now, if you look closely, the two CH2 groups in the middle are identical. So we can make it even more compact by writing it as CH3, parenthesis CH2, close parenthesis 2, CH3. That way, we're keeping the same information, but in a much more efficient form. Now let's see how to represent a central carbon with multiple identical substituents. If a carbon is bonded to 3 CH3 groups, we write those 3 CH3 groups inside parentheses and place the central carbon right next to them. This way, the notation stays short and clean, but still clearly shows how the molecule is put together. Let's look at another example. Here, the first two carbon atoms from the left are written as CH3 and CH2, and then we have a carbon that's bonded to both a hydrogen atom and a CH3 group. In this case, we write the carbon first, then the hydrogen, and finally, we put the CH3 group inside parentheses. Now, you might remember we also used parentheses in N-butane, like in CH3, parentheses CH2, close parentheses 2, CH3. But there's an important difference. In N-butane, the parentheses are used to show a repeating CH2 chain, but in this example, they're used to indicate a substituent group attached to that central carbon. So, same symbol, different purpose. What if a molecule contains a double bond? In condensed structures, the double bond can either be shown explicitly for clarity or left out, depending on the context. Both approaches are totally fine. It really comes down to how much detail you need to show in that particular situation. Now, let's break down another example. All the way on the left, we have two chlorine atoms attached to the same carbon, and that's written as Cl2C. As we move to the right, we see repeating CH2 units, so we enclose those in parentheses to keep things compact. There's also an oxygen atom in the middle of the molecule, and it's placed between the two carbon atoms it's connected to, right where it belongs in the sequence. Then, on the far right, we've got 3 CH3 groups, all attached to a single carbon. So just like before, we write the central carbon first, and then place the 3 CH3 groups inside parentheses. This makes the condensed structure look much cleaner and more concise, while still showing everything we need to know. There's one more thing to keep in mind. The way we write substituents can change depending on where the carbon atom is in the molecule. When identical substituents are attached to the leftmost carbon, we usually write the substituents first, followed by the carbon. But for all the other carbon atoms, we do the opposite. We write the carbon first, and then list the substituents that are attached to it. So make sure to watch for this pattern, because it definitely affects how the structure is read and interpreted. Finally, let's take a look at functional groups that include a carbonyl group, written as CO. For ketones, you'll usually see the CO group placed right in the middle of the condensed structure. Now, carboxylic acids. like COOH, and esters, which have a COOR group, contain both a CO double bond and a CO single bond. So in condensed form, they're written as COO or sometimes CO2. But there's one exception, aldehydes. Instead of writing them as COH, they're almost always written as CHO in condensed structures. And that's it for condensed structures. It might feel a little tricky at first, but with a bit of practice, it really does become second nature. Once you're comfortable reading and writing these, a whole lot of organic chemistry will start to make a lot more sense. All right, great job today, and I'll see you in the next lecture.